Hey guys, welcome to the lesson that we're going to look at today, volume by cross sections. So we're just continuing doing volume just like we were before, except instead of using the washer and the disk method, we're going to find the volume by having cross sections. Well, what is a cross section? A cross section is kind of like if you have a shape and you slice it, or you have an object, a three-dimensional object, and you slice it. You would get, so think about like a loaf of bread. If you take a loaf of bread that's not cut yet and you cut a slice of bread out, that piece of bread would be a cross section. It's going to be a piece of something that we're looking at. So here what we're going to do is we're going to see examples where we make our cross sections either be semicircles or squares. Those are the two that I'm going to limit us to for what we're doing. So in order to do this, what we need to first do is we need to make sure that we understand what area is of our cross section. Okay, because in order to find the volume, we're going to have the area and then times a height to get to our volume. So let's look. If we have a semicircle, if we want to find the area of this semicircle, well, what we need to understand is this S right here, this is going to be lying flat on the region provided. And the semicircle is basically going to be projecting off of our paper. Okay, if you look at this paper, the picture right here, you can kind of see that the semicircles are three-dimensionally coming off the paper. So the S is the side that's laying flat on the region. Basically, it's the part that's going to be in the area where we shade. Okay, so this whole side, S, well, we know that that's the diameter of a circle. So if we have a semicircle, we can think about it as our radius doubled, right? Okay, but what we want to do, okay, let's say this is the center. Okay, so from here to the right, that would represent the radius. If we were going to say what the radius is of a semicircle, well, the radius of a circle is pi r squared. So the radius of a semicircle is half of pi r squared. But here, we don't really have r, we have s. So we know that the radius is actually half of the diameter, which is s. So what we're really going to use here is 1/2 times pi, and instead of r, the radius is half of that diameter, which is s. So s half squared. Okay, so we can simplify this further. It's not necessary. We can always pull this 1/2 out to the front. You may see this sometimes written, if we square s, we get s squared, and if we square 2, we get 4. So then if we multiply the 1/2 by the 1/4 here, this would be the same as having 1/8 and then pi and then just s squared. Okay, so we can use either one of these. It's just whichever one you're more comfortable with. Okay, now let's get the area for a square. So if we use our cross sections as squares, okay, well that means we need the area of the square. Well, we know that the area of a square is length times height. And if it's a square, my length and my height should both be the same. So that means it's going to be s times s, which is s squared. So that one's really, really easy. Okay, so let's take this in an example and let's kind of work through this. We have, this is our picture here. So it says we want to find the volume of a solid whose base is bounded by these two functions, y equals x and y equals negative x, and the line x equals 4. And we want the cross sections to be perpendicular to the x-axis, and they're going to be squares. Okay, first, this perpendicular to the x-axis. If something's perpendicular, it makes a 90-degree angle. So that means every single time we create a square coming off of this, okay, it's going to need to have this Okay, because notice what we're doing here is we're crossing the x-axis, so it's perpendicular. Okay, so really what we're going to do is we're going to get a three-dimensional square coming off of the grid at that one spot. Okay, so what we need, we're going to say that this length of the side of the square is going to be from here to here. Well, we can represent the length of S the same way that we've been representing the length of our radius when we've been revolving around an axis. This is always going to be top minus bottom or right minus left, depending on which way we're doing. Okay, so here we've got the top function that S line is touching, okay, which is x. And then we're going to subtract the bottom equation that line is touching, which is negative x. So this is going to give us x plus x, which is 2x. So that means the length of this side of the square is going to be 2x. Well, we know that the area of a square is going to be the side of it squared. So we're going to have 2x squared. Okay, to find the volume of this square that's projecting off the page, well, we need its area, which we just found, and then we also need the width of it. Okay, to get the width of it, well, the width, just like before, dx represents the change in x. So whatever the width is of that x, we're going to represent with dx. Okay, and so that kind of gives us the area times the width of that cross section. Now, if we have a dx, we have to have an integral. The integral here is saying that we're going to do this square repeatedly an infinite number of times. Well, from when to when? Well, if this is going perpendicular to the x, everything's in terms of x here. So my smallest x is 0, and my biggest x here is 4. Okay, so all we really need to do is we're doing an integral of the area of our square. Okay, so I'm typing in right now into Math 9 the integral from 0 to 4 of 2x squared and then dx. Okay, and I am getting, when I do that, that the volume is 256 thirds pi. I'm sorry, no pi. There's no pi on this. Just 256 thirds. So that is the volume in which we want to create these coming off the page. Okay, so let's look at a different example that's not a square. This time it says we're going to find the volume of a solid whose base is bounded by the graph y equals the square root of x, that's this one, and x equals 9, which is this one, and the x-axis, which is here. So therefore, this is our shaded region. We have cross sections that are perpendicular to the x-axis. That means it's going to go this way again. Sorry, that line is not very straight. And this time, we're going to make them semicircles. Okay, so this line right here is going to be S of my semicircle. And from here, my semicircles are going to protrude from this page. Okay, and we're just going to get an infinite number of those over and over, giving us this three-dimensional object that's coming off the page. Okay, so we can determine what S is. It's the length from top to bottom. So top function, square root of x, minus bottom function, which is 0. Okay, then let's find the area of that cross section. So the area of my semicircle. Okay, remember my semicircle was 1/2 times pi. Then we had our s, which is square root of x here, divided by 2, and that is all being squared. If we want to clean this up, if you square the square root of x, you get x. If you square 2, you get 4. Okay, that 2, the 1/2 here, the 2, and the 4 that became from 2 squared gives us 1/8 pi, and then when we squared that square root, we just got x. Okay, so this is our area, and then we want to make it now the volume. So the volume is going to be the integral. My lowest x is 0, my biggest x here is 9. And what I'm going to do after my 9 here is I'm going to take the 1/8 pi, or pi eighths, and I'm going to put that on the outside because remember that's just a constant, so we can move that out. That just leaves me here with an x, and then dx, which is the width of every single one of these cross sections. Okay, so for this, I'm going to go ahead and work this one out by hand just as a reminder for you guys. So we've got pi over 8. Then when we take our antiderivative of x, we increase the power by 1, divide by that power, and then we're going to evaluate it from 0 to 9. So we still have the pi eighths out in the front. Okay, then we get 9 squared, which is 81. And that's over 2. Okay, and then when we subtract, we're really subtracting a 0, so I'm just going to kind of leave that at that. And we end up getting that the volume here is going to be 81 over 16 pi. Okay, so therefore it stays in the exact form because it's still got the pi in it, so we know. Okay, so here now we're doing a different example, a different graph, but we're going to do a square and we're going to do semicircles, and both of these are going to be perpendicular to the x. So remember, for a square, the side that lies in the region is always going to be top minus bottom. So the top function here is the x plus 1. The bottom function here is the x squared minus 1. That is going to give us a negative x squared plus x, and then 1 plus 1 ends up being plus 2. Okay, well, we know that the area of that square is just going to be this trinomial squared. And then our volume, okay, is going to be the integral. So our smallest x here is -1. Our biggest x here is 2. Then we're putting our area in here. And dx for the width of every single one of those cross sections. Okay, I'll let you go ahead and type that in. Let's go ahead and set up the next one, and then we'll put those answers up. Okay, so we're going to do the side that lies in the region for a semicircle. Same thing, we're still going to have the same side. So it's still going to be top minus bottom. So we're going to get the same that we got for the other one. So negative x squared plus x plus 2. The area on this one is a little bit different. Okay, so remember, we've got this ended up being pi eighths. And then our s squared. So all of this squared. And then we're going to plug that into the volume. Our integral is still going to be from -1 to 2. I'm going to put the pi eighths out in the front. And that way just this piece being squared is on the inside. That rest of the area. And then my dx. So go ahead, take a moment, type both of these in, and then check your answer. All right, the first one ends up being 81/10, and the second one ends up being 81/80 pi. Okay, have a good one.